Okay, we continue with example on uh, first law analysis for combustion. So basically what we want is actually want to determine heat transfer due to combustion. Okay, if you notice, this is actually continuation from the previous example, right? So with a 50% excess air combust together with the liquid propane C3H8, and the fuel temperature is 25 degrees C, the air is 7 degrees C, produce CO2, H2O, N2, CO, and O2. And the product gases is 1500 Kelvin, right? So this is the balance equation from previous, and no need for us to determine the mass flow rate. We have determined this before. Alright, so this one we want to determine Q dot, the rate of heat transfer from the combustion chamber. Okay, so from energy balance, right, from the Q up equals to HR minus HP, right? This is from the energy balance that we've done before in the previous lecture. So since you know enthalpy and R, you need to find the enthalpy of formation plus the enthalpy at the state minus the enthalpy of reference state at 25 degrees C. Okay. So this one minus the HP, which is NP HF plus H minus enthalpy at the reference state for product. Okay, so this is what we're gonna do. We're gonna create a table, which is first is the all the substance involved in this combustion. Next is the enthalpy of formation, and then we have enthalpy at 280 Kelvin, and then next is enthalpy at 298 Kelvin, and then enthalpy at 1500 Kelvin. Right. Okay. So let's make it a table. Right, nice. Okay, next we list out the substance. First is the fuel, right? So which is C3H8, and then the oxygen, part of air, and then the nitrogen, and then we have H2O. So gas, not water vapor. It's actually gas. I mean, not liquid. Okay, not moisture. It's actually water vapor, gas. right? And then CO2, and then CO. Okay, alright. So first we need to find the enthalpy of formation for each substance. So what we need to refer to the property table, table A 26. So oxygen, so this one, oxygen, nitrogen, and we have H2O, right? Water vapor. Okay, not liquid, not moisture, because dry. So we list out those and put it into our table. So sorry. Okay. O2 is 0, N2 is 0, and then H2O, 241,820, 241,820, and we go to CO2, carbon dioxide, 393,520, 393,520, so negative, 393,520, and then carbon monoxide, negative 110,530, negative 110,530, and then C3H8 is given heat of formation negative 118,910, negative 118,910. Okay, this is the enthalpy of formation for each substance involved in this problem. Alright, so next we need to determine the enthalpy at state 280 Kelvin, 298 Kelvin, and enthalpy at 1500 Kelvin. Before that, why 280 Kelvin, 298 Kelvin, and 1500 Kelvin is because of based on the temperatures of fuel, air, and product. Okay, so 25 degrees C meaning 298 Kelvin. Air is 280 Kelvin, and then the product is 1500 Kelvin. Alright. Okay, for enthalpy at 280 Kelvin, which is air, right? Only air operates on 7 degrees C. So meaning there is no C3H8, no H2O, no CO2, as well as no carbon monoxide. Okay, so we just need to find the value at for oxygen and nitrogen at 280 Kelvin. Okay, so O2, so we use the ideal gas properties for O2. This one is table A19. So 280 Kelvin is 8150. And then for nitrogen, 280 Kelvin is 8151. So we put those values into the table. 8151 and 8150. So go to right. So next is for 298 Kelvin, right? So let's take a look at enthalpy of oxygen at 298 Kelvin. So 8682, and then for nitrogen is 8669. So similar approach, you list out all the enthalpy of other properties, or I mean other substance for which 290 Kelvin. So this one is 8682, 8669, and then water is 9904. This one is 9364, and CO is 8669. So for fuel no need, because it occurs at, because later it occurs at a reference state, so you're gonna minus out the value. So at 1500 Kelvin, right, this one, no, and then we have to find O2, N2, H2O, CO2, and CO at 1500 Kelvin. For example, let's go for N2. 1500 Kelvin is 47,073. Okay, and then for N2, sorry, O2, 1500 Kelvin produce 49,292. 49,290. Okay. So similarly, you find for other values. Seventy-one thousand 708 and 47,570. Okay, done. So next you calculate for H reactant. So H reactant is the total of N R and the enthalpy of formation plus H at 298 Kelvin minus H at 298 Kelvin. So what we have is actually C3H8. So the number of moles based on this is 1, right? So for C3H8, 1 particle is H enthalpy of formation negative 118,910 plus 0. This one is plus H298 Kelvin minus H298 Kelvin. So that's going to be 0. And then we have 7.5, right, for oxygen. 7.5 multiplied with enthalpy of formation for oxygen is 0 plus 298. Okay, so for this one is no, this is valid for, okay, for this one is an R HF. So for oxygen, it occurs at 7 degrees C, right? So H280 Kelvin minus H298 Kelvin. H280 Kelvin minus H298 Kelvin. So plus 8150 minus 8682. Okay. So next is nitrogen. Okay. Because reactant, nitrogen also part of reactant. So if we look here, 7.5 multiplied with 3.76. 7.5 multiplied with 3.76, and similar with this one, because nitrogen also occurs at H280 Kelvin. Enthalpy of formation is 0 plus 8141 minus 8669. So if you calculate this one, you produce the enthalpy at reaction. So next is product. Okay. So for product, make it smaller. So for product, we start with carbon dioxide. So this one is 2.7. So carbon dioxide enthalpy of formation is negative 393,520, and then plus H. Now it occurs at 1500 Kelvin because all product occurs at 1500 Kelvin. So for carbon dioxide is 71,078. So minus 9364. Okay, and then plus now we go for CO 0.3. So carbon monoxide enthalpy of formation is negative 110530, and then plus 47517 minus 8669. Okay. That's for carbon monoxide. Then we go for H2O. So for H2O, the number of moles is 4. H2O enthalpy of formation is 241820. So right, and then plus 57,999 minus 9904. 90. Okay. So that's for H2O. Okay. Next we calculate for O2. Okay. So O2 is 2.65. The number of moles 2.65 multiply with 0, the enthalpy of formation, and then H at 1500 Kelvin is 49292 minus 8682. Okay, and then the last one is nitrogen 28.2. So multiply with enthalpy of formation 0, and then plus 47073 minus 8669. Okay, so you determine this value. So next what we need to do is determine the HQR. It's actually HR minus HP. Okay. So from there, 363,880 kilojoule per kilo. Okay, next if you want to find the value of Q in terms of kilojoule per kilogram, right? So we need this Q up divided by the molar mass of fuel, which is 363,880 divided by 44. Okay, go to the floating table. Table A27. Okay, so for propane is 44. So from there, you're gonna get this value equals to 8270 kilojoule per kilogram. Okay. Next, if you want to determine Q dot, right? Since the mass flow rate of Q dot is given 0.05 kilogram per minute. Okay, so Q dot is actually Q multiply with M dot. This is R multiply with M dot. So 8270 multiply with M dot 0.05. This is kilogram per minute. So from there you can determine 413.5 kilojoule per minute. And if you convert into kilowatt, kilojoule per second, you can produce 6.989 kilowatt. Alright. Okay, so there you go. That's how actually we determine the rate of heat transfer from the combustion chamber. So I think that's all. Assalamualaikum warahmatullahi wabarakatuh.